Alright, so in this video we're going to talk about the normal distribution. So we say that x has a normal distribution with parameters mu and sigma if its PDF is given by this expression. So we have 1 over the square root of 2 pi sigma squared e to the minus x minus mu quantity squared over 2 sigma squared. We typically write x as n, or we typically write x as n of mu sigma. So let's say normal of mu sigma. So the normal distribution is probably one of the most important distributions you learn in probability and statistics. One of the things that we'll see at the end of the semester is something referred to as the central limit theorem. And the central limit theorem says that no matter what distribution you have, if you take samples, enough samples, and look at the distribution of the sample means, it's always approximately normal, no matter what. So you'll do a lot of work with normal distribution in any statistics class that you ever take. Alright, if mu is 0 and sigma squared is 1, then we refer to x as saying it has a standard normal distribution, and typically we're to denote the standard normal distribution by z. To check that we really do have a PDF here, we would need to integrate that function from the previous slide over the support and show that it actually is equal to 1. We should also note that the function is non-negative, but since the only place that x is going in here is in an exponent, e to any power is always positive, so we don't have any worries about this ever being 0 or negative. All right, so to integrate this, let's do a u substitution. Let's let u equal x minus mu over the square root of sigma squared. So basically the part that's inside the squaring here. The derivative will just be 1 over the square root of sigma squared. We notice we've already got that out in front here, this without the square root of 2 pi part. Notice also that as x goes to negative infinity, so will u. As x goes to positive infinity, so will u. So we make the substitution here. We still have integral from minus infinity to infinity. We get 1 over square root of 2 pi e to the minus u squared over 2. And that we saw, we computed in a previous video. This is exactly square root of 2 pi. So we get 1 over square root of 2 pi times square root of 2 pi, which gives us 1. Let's find the moment generating function. We're going to calculate the expected value of e to the tx. That's taking the function times the PDF over the support and integrating over the support. And let's combine the exponents here. So we're going to focus on the exponent here with this tx minus the x minus mu squared over 2 sigma squared. Let's get a common denominator. So that's where the 2 sigma squared is coming from on the tx. And then let's factor off a negative 1 over 2 sigma squared. One thing that we notice is that we've got 2 terms that have an x in it, so we'll factor out the 2 and the x off of those things. So we get x squared minus 2 times the quantity mu plus sigma squared t times x plus a mu squared. And again, these signs are flipped because we factor out a negative sign. Now we're going to complete the square here in the exponent. So remember, to complete the square, we take half the coefficient on the x and square it. That's where this mu plus sigma squared t squared is coming from. Now, of course, I can't just randomly stick this in here and not make sure things are equal. If you square this part out, you'll get a mu squared, which we have. But we'll also get a 2 mu sigma squared t and a sigma to the 4th t squared, which we don't have. So I need to subtract that off the end here to keep everything equal. Then if we rearrange things, in particular, split it right here at this minus sign and flip the order, we'll get a mu t plus sigma squared t squared over 2. That's this piece times the negative 1 over 2 sigma squared. And then we have the negative 1 over 2 sigma squared, and then this first 3 terms factors as x minus half the coefficient on the x, the mu plus sigma squared t, quantity squared. Let's go back to the integral, plug that stuff in. That's what this mess is here. Let's split into pieces. Let's split it this minus sign. This part has no x's in it, so it's a constant, so I can bring it out in front. This looks exactly like the PDF for a normal distribution, except that we replaced this mu plus the mu with the mu plus sigma squared t, which there's nothing wrong with that. This really is a PDF of a normal distribution. It's just got a different mean. So that integral is going to be 1, which we just showed in the previous slide. So this is our moment generating function. Now we can find the mean and the variance. Take the derivative. Derivative of e to a power is e to that power times the derivative of the power. Notice that this really is the derivative of the power with respect to t. Plug in 0 and we really do get mu. Second derivative is going to require a product rule. Got to take the derivative of the first, which is the segment squared. Got to take the derivative of the second in the second part here, and another mu plus sigma squared t pops out when we do that, which is why it's squared. Plug in 0, we get mu squared out of the first term, and we get sigma squared out of the first term and mu squared out of the second term. And then use our variance formula to calculate the variance to get sigma squared. Now, when working on problems with a normal distribution, frequently we're going to convert things over to the standard normal. And the way we do that is with this formula. With any normal distribution, we can convert using this x minus mu over sigma, and it's going to give us a normal distribution on 0, 1. Much like we've talked about in class and in other videos, we're going to attack this by looking at the CDF. We're going to replace the z with the formula for z in terms of x, solve the inequality for x, plug it into the CDF of x. Now let's do a u substitution, same substitution that we did on the previous slide. Notice as x goes to negative infinity, so does u, but when x is mu plus sigma z, all we get is z for that upper limit. Looking at this expression, this really is the normal distribution, a CDF for normal distribution with a mean of 0 and a variance of 1. So z really is standard normal. Instead of using a capital F, we typically write a capital Phi for the CDF of the normal distribution, and we will use that notation a lot in class. We mentioned on a previous video that the chi-squared distribution is exceptionally important. It will be very, very important next semester in your statistics class. So one of the connections between the normal distribution and the chi-squared distribution is that when you square a standard normal, you get a chi-squared on 1 degree of freedom. That's what this theorem says. So let's go through the details. Again, let's appeal to the distribution function of z squared. So again, we want the distribution function of w, plug in the function of z squared that makes up w, rewrite our inequality, and then rewrite that as an integral. So we know the PDF for z, we know that z has to be in between these two bounds of z squared is going to be less than or equal to w. That's how we calculate probability in that case. Now we notice that this e to the negative z squared over 2 is symmetric about the y-axis. So I can replace this integral with 2 times the integral from 0 to root w of the integrand. Now let's do a substitution here. I'm going to let u equal z squared, then du is 2z. Now, of course, I don't have a 2z. I do have a 2, but I don't have a z. So if I divide both sides by a z, and then solve the equation up here for z, I would have z equals square root of u. So I get du over root u equals 2dz. So the 2dz becomes the du, and then I have du over root u, well, that is just u to the negative 1/2. So I have this PDF, which I can split up a little bit more as 1 over square root of pi times 2 to the 1/2, u to the minus 1/2, or u to the 1/2 minus 1, and e to the minus u over 2. Now remember what our PDF looks like for the chi-squared distribution. This has to be gamma of alpha. Well, square root of pi is gamma of 1/2. So if I look where the alpha is supposed to be in the chi-squared distribution, the 1/2 is r over 2 in that case, so the r is 1. I have it here, 2 to the r over 2, so 1 over 2 here. I have it here, u to the r over 2 minus 1 in both of those spots. So I really do see the chi-squared distribution here with 1 degree of freedom. So the r here would be replaced with the 1 here. We're going to do more problems with these in class, but this gives you the theoretical background in the normal distribution and how it connects to the chi-squared.